Hey there, everybody. Welcome back to another episode of Calculus 1. And we're going to work we're about to the end of Calculus 1 here, one of the most important processes that we do in Calc 1, however, prepping us for the adventure of Calculus 2. And that is the concept of substitution, integrating by substitution. It's called U sub in some textbooks, U substitution. It's called change of variables some places. But the idea is that we are undoing the chain rule. And so if you remember what the chain rule said when you take the derivative of f of g of x, then you get the derivative of the outer function times the derivative of the inner function. And so we're looking to apply this rule to things that look like this, where we have two functions multiplied by each other. One of them is clearly inside of another one, and then its derivatives hanging around. We're a facsimile of its derivative anyway. So I'm just going to work a few examples. You can find the introduction to the concept of U substitution also on my YouTube channel. It's just a different video. This is part 2 kind of, and just showing you guys how to integrate. So we're going to go through the process here of 5 different problems. I'm going to try to bounce back and forth, and I'm going to walk through it in the step-by-step process that I instructed my students to do in class. Hopefully that will provide you with some ideas. So the first thing you want to do here, however, anytime you get a square root, unless it's a rule that uses a square root like arctangent, I'm going to rewrite this as x cubed minus 1 to the 1/2 power, because I want to think of this as stuff inside of another function, right? It's inside the square root, but I don't have any square root rules except for the rule that is for arctangent, and that's not going to apply here because it's not in the denominator. And so this must be a rule for the power rule. And so we rewrite it as a 1/2 power. And then as I've chosen here, you can see that the function inside of another function, inside the g of x function, that's what we call u, right? U is going to be x cubed minus 1. So that's, again, there will be times, guys, when you make bad choices for u. And if you do, you just have to come back and start over. But in this case, it's pretty obvious u equal to that is the right choice. And so that's the first step. And now here's what I want my students doing anyway. I want you to go back and plug in so that you see what you have left, and you plug in for u to the 1/2. And probably even better, to be honest, guys, is to rearrange. Here's the u part. I have u to the 1/2, and then what's left over is x squared dx, right? So I've just rearranged these guys and paired them up, okay? So that's step 1. Step 2 is not up to me. I got to choose u. That was my choice. Once you choose u, you're committed to it. So now you have to take the derivative, du dx. I'll take the dx to the other side. And the derivative of x cubed minus 1 is 3x squared. Okay, and so now I take a look at what is here compared to what I have left. Are they the same, or are they really close to each other? In other words, is the only difference a constant? And in this case it is. The only difference is a constant. So I can divide both sides by 3 and get 1/3 du equals x squared dx. But I want to make sure that I'm substituting exactly for what I have, and I have exactly x squared plus, or x squared dx. So I'm going to substitute 1/3 du for that. So that's come back over here again. And I am left with u to the 1/2, and then 1/3 du goes in here. Okay? And then, of course, we could take a 1/3 out because it's a constant. All right, and now's the key point, guys. This is step 3, and this is the big step. Okay, this is the big step here. Is this something I can integrate with my basic rules? right? You should have some basic rules from our textbook. It's section 4.9. We had all those basic rules, and this is the power rule. Okay, and so if I can do it, then I do the rule right now. All right, I joke around about do the rule, but that's what I do. That's what my turn, and that's what this symbol means, and that's what this symbol means. And so when I do the rule, and the rule is what? Well, the 1/3's already there. What's the rule for u to the 1/2? I add 1 to the power, so I get u to the 1/2 plus 1, divided by 1/2 plus 1. I get a plus c. And this symbol here and this symbol here are all gone because because I did the rule, right? When I do the rule, that's all gone, okay? And then I want to rewrite this a little bit. This is 1/3 u to the 3/2 divided by 3/2, okay? And of course, the 3/2 dividing by 3/2 like multiplying by 2/3. So if I multiply by 2/3 times 1/3, I get 2/9. U to the 3/2 plus c. And then step 4, don't forget step 4. Step 4 is it's not about you. All right, I like to throw that phrase out there. It's not about you, right? It's about the x or whatever the other variable was up here. And so I substitute back. And if I have to go back up here, I take a look and remind myself what u was. U is x cubed minus 1. And so I plug in for u with x cubed minus 1, and I get 2/3 or 2/9, x cubed minus 1 to the 3/2 plus c. That's my final answer. And if you want to check it, you certainly can by taking this derivative using the chain rule and seeing if you get back to the original function. And if you do it properly, you will. Okay? So that's the process. I'm not going to step through each process like I did this time. I'm going to just do the rules now for the next 4 examples. I'm not going to accentuate part 1, part 2, all that kind of stuff. I'm just going to move forward. So if you need to come back and pause this or watch this video, this part of the video again, then certainly allowed to do that. Problem 2. Here we've got an issue because we've got 2 different rules that we need to use. And so I'm going to use the fact that I can break up my function here, and this is not right. This should be a secant squared. It's supposed to be a secant squared. All right, dx minus, we can do secant, but we're not ready for it, so I'm not going to make you do it. It should be a secant squared, dx, and then I've got an x e to the x squared dx. And so what happens here is we actually have 2 integrals, so we're going to get 2 u's. Now you can do separate u's or you can do a u and a v. You can do different letters if you want, but I'm just going to do the problem twice. So over here for this u, what do I need u to be? I just need u to be the inside function. U is 3x. And so I get the integral of secant squared u, still dx. Take the du. I get 3 dx. I don't have a 3, so I divide both sides by 3. I get 1/3 du is dx. And so I pull the 1/3 out and get secant squared u du. And again, I haven't integrated yet. I haven't done any calculus yet. This is just algebraic substitution. Over here, I'm going to do a different u. All right, let's put it in a different color. And so I'm going to do a u equal to x squared. Why did I pick x squared? Because that's the power of e, and we know e to the u is a rule. And so the power of e is actually what's inside of another function. The function's e to the x, so we have x squared inside of that. So when we put this integral together, we get e to the u, and then what's left? What's left is x dx. I'm going to take the du. I get 2x dx. I don't have a 2. I just have 1. So divide both sides by 2. All right, and then I pull out the 1/2, and I get e to the u. This gets substituted by 1/2 du. The 1/2's out front, du. Okay, so I'm going to draw a red line here to represent that I'm done substituting. This is the new idea. This is the u substitution, right? Change of variables idea. Everything above here, everything up here is the new idea. So if you have any problems from now on, this is not the new stuff. This stuff is now we're going to do 4.9 stuff. What's the antiderivative rule for secant squared? The antiderivative of secant squared is tangent u. What's the antiderivative of e to the u? E to the u, right? Derivative of e to the u is e to the u. The antiderivative is e to the u, and so I get e to the u plus c. And then I need to substitute this u back in here, and I need to substitute this u back in here. All right, so I go back into it, get rid of all my colors, and I get 1/3 tangent of 3x, the appropriate one, minus 1/2 e to the x squared, using this appropriate one, plus c. And there it is. So while you don't have to really break this up into two different integrals, you do have to worry about two different u's. This is one u and this is a different u. And so you've got to either use a u and a v maybe, or you've got to break it up into two integrals and do this one as a separate problem and this one as a separate problem, okay, with this u here. All right, that's problem number 2. Problem number 3. I look at this and I don't see anything inside of another. So now I have to think about my rules, right? My rules, I have a power rule, I have all the trig function rules, I have e to the power, and I have 1 over u du. That's one of my rules. Well, this certainly could qualify for that because this down here is stuff over t squared plus 4. Now, I also have one other rule, and that's the arctangent. That looks something like this. How do I know? All right, how do I know which of these is the appropriate one? Well, look here, this is t squared plus 4, which is basically this two things squared. Remember that the variable is always u, so even if u is on the right or on the left, t is still the u, right, if you're doing arctangent. And 4 is the a squared. The constant's always, it doesn't matter because it's adding, it doesn't matter what order it's in. But this has a constant on top. This does not have a constant on top. This has a t up here. So because of that t up there, that tells me I probably need to look at this rule because I have no way of getting that t out of there if I try to do arctan. All right, so let's try that. Let's try, and again, you're going to make mistakes, especially as you start. Math is not for quitters. Calculus is definitely not for quitters. And so you need to pick a u, and it may work and it might not. And if it doesn't, you try something else. Okay, so I'm going to let u be the bottom because I have this rule that lets u be the whole bottom. And so what does this look like then? If I let u be the bottom, then this gives me 1 over u. I'm going to pull this 6t out to the side and get 6t dt. Okay, so how's that going to work for me? Well, let's take a look. This is du, take the derivative. The derivative of t squared is 2t, the derivative of 4 is 0, so I get 2t dt. Is that what I have? No, I have 6, not 2. Well, just multiply both sides by 3, right? If I multiply by 3, 3 times 2 is 6, so I get 3 du's, has to be 3 times 2, 6t dt. All right, so just like I divided last time, now I'm going to multiply to get 6t. And if you didn't see that, you could divide both sides by 2 and substitute in and combine the 2 and the 6 later. But anyway, so I'm going to substitute this here and here, and I'm going to end up with the integral of 1 over u, 3 du. Remember, guys, we're not, it's called a change of variables, but we're not changing. We're substituting. You can't just change because you feel like it. Hey, I don't like dt. Let's make it a du. You can't do that. All right. What you can do is you can say this is equal to that. So since they're equal, I can stick one of them in as a substitution for the other one because they were the same. Right? You do a pick order at Walmart and they don't have one brand of refried beans, but they have a different brand of refried beans. They will substitute one for the other because they're basically the same thing. These are basically the same thing. So you can plug one instead of the other one. You can do a substitution. Okay, you can't substitute if they're not equal. So then the 3 comes out front, and so now the question is this one of my rules? Absolutely it is. So you do the rule, right? Here's the key. This is the key step. Do the rule. What's the rule? The rule is natural log of absolute value of u. And now it's not about u. Step 4, plug back in. Some of your textbooks would not have the absolute value here. Why is the absolute value missing? Absolute value would have been fine, and I would take it correct. Okay, but your My Math Lab or whatever might not use it. Absolute value is equal to regular t squared plus 4 in this case because, why? Because t squared plus 4 is never negative, right? T squared is always non-negative, and plus 4 makes it always positive. T squared is greater than or equal to 0. So t squared plus 4 is definitely greater than definitely greater than 0, and so you don't need an absolute value. And that's why. All right. So that's the answer for number 3. Now take a look at number 4. Here's 3, 6t over t squared plus 4. Here's 4, 6 over t squared plus 4. That's 6. That 6 doesn't need to be in there. I mean, you could keep it in there, but it doesn't need to be in there. But if I pull this out, what rule does that look like? Remember, I had the 1 over rule, and I had the 1 over a squared plus u squared rule. This is natural log. We just used it. But if I let u, I'm going to write it in red because this is not right. If u was t squared plus 4, then du would be 2t dt, and there's no t. It's okay that there's no 2, but there's no t. And you can't, if you divide by the 2, that's great, but if you divide by the t, this can't come out. All right, I talked about in my last video that this integral symbol is kind of like a semi-permeable membrane. And so what that means is that nice simple things like constants can come through it, but complex things like variables cannot make it through that membrane. And so you can't pull out a 2t, you can't do it. Okay, so let's go to regular colors here, and we're going to make this, we're going to try to do, what are we trying to do? We're trying to do a squared plus u squared is arctan. We're trying to do that rule. And this is why it's important that you know your rules, right? So that you know what you're substituting for. Okay, there's a plus c here, obviously. So what's playing the role of u? It's the variable. U is equal to t. And then what's playing the role of a? A is equal to 2. Because a squared has to be 4. So as a is equal to 2, u is equal to t, and since u is equal to t, du and dt are the same. So this guy becomes 6 over 1 over u squared plus 2 squared du, if we go into it. And if you know the formulas, guys, and you recognize the formula, you can go straight down and you don't even have to do u substitution for this particular problem, but just in case, all right? So what's the rule? The rule is 1 over a is equal to 2, arctan of u over a plus c. Simplify, 6 times a half is 3, and then plug back in for t for u, t for you, t for me. So 3 arctangent of t over 2 plus c. Now again, that looks so close to this integral. It takes practice, guys. Do not, I mean, I'm just flying through this because I know what I'm doing, because I've done so many of these problems, but you have to make that commitment. You have to practice, 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 practice these problems. Absolutely got to practice them. Okay, so let's take a look at one more example. All right, so take a look here. We have e to the stuff, and then we have some other stuff multiplied. Now you could think of this as secant of x all squared, but I think it's more important that you look at this and think of this as e to a power. Look at the power. If u was equal to the power, and guys, this is one way to pick your u. One way to pick your u is it's obviously inside of another function, but another way of picking your u is how does it relate to what's left? If I pick u equal to tangent, what's du? The derivative of tangent is secant squared. So that's a wonderful confirmation, right, that this is probably a good choice for you. So u goes up top. I have secant squared x dx in the bottom. Again, once you get really good at this, you're going to be able to do both of these steps over here at the same time, but I don't recommend it yet. Replace that here, with what? With du. And so I end up with the integral, the antiderivative of e to the u du. They match perfectly, no numbers, no nothing. And then what's the rule? Do the rule, e to the u plus c, and take it back. E to the tangent of x plus c. Okay? And that's the way it goes. Now, with all of that being said, I want to show you one more problem, one more example that rarely happens. Okay, let me add on a page here. This is a special case. You won't see this very often, but boy, you better see it once at least. Okay, special case. And I'm going to do the integral from x times x plus 2 to the 5th dx. Now, you could theoretically, all right, you could theoretically multiply this out 5 times and then distribute the x. So that'd be horrible. I'd hate to do that, okay? So what I'm going to do is I'm thinking this is stuff raised to a power. It's an obvious choice for you, right? This is obvious. X plus 2, simple enough. And so this becomes the integral of u to the 5th, substitute. What's left? The x is left, and the dx is left. That's what's left. So that's what I have. So then I just take my derivative here. Take my derivative, please. du is 1 dx. Huh. That doesn't take care of everybody. I mean, I get rid of the du, right? I get a du here. So I at least get that. So let's go ahead and substitute it in and see what I got. I got u to the 5th. I got an x hanging out, and then I have a du. So I substitute it in here. I substitute it in. There's still this x hanging around. And I just talked about semi-permeable membranes, and x is too complex to pull out. You can't do it. A u to the 5th, I got a du, but I still have an x. I'm stuck. Well, I'm not stuck, and that's only because I know what to do. I'm not stuck because if u equals x plus 2, what happens if you subtract 2 from both sides of this basic equation? If you subtract 2 from both sides of this basic equation, you solve for x. You get x is equal to u minus 2. Well, if you're going to go u, you might as well go all u. And so I take this u minus 2 and I substitute it in for the x. Make sure you have parentheses. Okay? So I get integral of y to the 5th, or u to the 5th, u minus 2 du. Okay, now, is that one of your rules? No, it's not one of your rules. Well, what the heck? What was the point of doing all this if it's not one of my rules? Ah, here's the deal. Here, I cannot distribute the x because your dear Aunt Sally tells you that exponents come before multiplication. Distribution is multiplication. I cannot multiply in there because I have this power. Look what I have now. I have a group, but it's not raised to a power, which means I can take this u to the 5th and I can distribute it to u and distribute it to negative 2. And so I end up with u to the 6th minus 2u to the 5th. Are those rules that I can do? Absolutely. I've got 2 rules I can do. They're both power rules. So I add 1 to the power. I bring the 2 along, add 1 to the power. And now it's not about u. So I end up with x plus 2 to the 7th over 7 minus, reduce this to a 3 on the bottom, x plus 2 to the 6th over 3 plus c. And that, my friends, is a big ugly mess, but that is what you get when you anti-differentiate this simple little thing. Okay? So this is a very special case. It doesn't happen very often. Basically, the idea here is that you have 2 linear terms, x to the 1st power times x to the 1st power with stuff to a power. All right? If you have that situation, a linear term inside a power and another linear term sitting outside, that's when you're going to do this special case of solving for x and plugging in and seeing what happens. Okay? Again, you won't see that very often. You might see 1 or 2 problems like that in the homework, but you got to be familiar with it, because it is a special case that does pop up on occasion. Okay, so I hope that helps, and I'll see you next time.